In this video, we will discuss two advanced features of VisSim Compound Blocks, enabled execution and local time step. Additionally, the local time step feature will be applied to implement the block diagram equivalent of a for loop to iteratively solve a nonlinear implicit equation. The enabled execution feature of a compound block allows you to control when, during the simulation, the compound block is executed. When the enabled execution option is checked, a round red-colored input pin is added to the compound block. This pin expects to receive a Boolean input. When the input is 1, the compound block executes. When the input is 0, the compound block does not execute. Its output is held constant at the value it reached during its last execution. To illustrate how the enabled execution feature operates, we'll construct a compound block that counts time steps. From the Block's Time Delay menu, select and place a unit delay block. From the Block's Signal Producer menu, select and place a constant block and connect it to the Boolean input of the unit delay. From the Block's Arithmetic menu, select and place a summing junction. From the Block's Annotation menu, select and place a wire positioner. Control-Shift to copy the constant block and connect the summing junction. Encapsulate the logic in a compound block named pulse counter. Add one output pin for the pulse count. Navigate into the pulse counter compound block and connect the output pin to the unit delay input. From the Block's Signal Consumer menu, add and connect a plot to the output pin. Under System Properties Range, set the time step equal to 0.01 seconds and end equal to 1 second. Click Go to simulate the model. Since the time step was set to 0.01 seconds and the end time to 1 second, the pulse count increases from 0 to 101. Now we'll modify the pulse counter compound block to only count pulses from time greater than 0.25 to 0.5 seconds and from time greater than 0.75 to 1 second. Right button on the compound block and check Enabled Execution. From the Block's Signal Producer menu, select and place a square wave block and connect it to the red circular Enable pin. Right-click on the square wave and set the frequency value to 2 Hz. We'll plot both the square wave signal and the pulse count in a plot block with the subplot count set to 2. Click Go to simulate the model. The Boolean square wave signal is shown in the upper plot in red. The pulse count signal is shown in the lower plot in blue. Since the compound block was disabled from time equals 0 to 0.25, it does not execute and the pulse count equals 0. From the time equal 0.25 to 0.5, the compound block executes and counts 25 pulses. From the time equal to 0.5 to 0.75, the compound block does not execute and the pulse count is held constant at 25, and from the time equal to 0.75 to 1, the compound block executes and counts 25 additional pulses for a total of 50. The local time step feature of a compound block allows you to specify the update time that the compound block is to be executed. Using our pulse counter example, let's use the local time step to see the effect it has on the pulse count value. Control-Shift left mouse to copy the pulse counter compound block. Control right button on the compound block copy. Check local time step, enter 0.1 seconds, click OK. Notice that the compound block turns to a light green color with a diagonal line pattern to signify it is operating under local time step control. Click Go to simulate the model. Observe the red compound block pulse count increases to 101 as expected. The local time step compound block pulse count is shown in blue. Since the local time step was set to 0.1, the block counts once every 0.1 seconds and achieves a final value of 10 pulse counts as shown. The local time step feature can be used to model multi-rate discrete systems, partition and solve stiff systems of equations at different time steps, and also to implement the block diagram equivalent of a for loop. In this example, we will solve the equation y is equal to minus 0.2 times the quantity sine of y times y squared plus x. We'll solve this equation for y, given the input value x, using the local time step option to program a for loop to solve the equation by iteration. First, we'll use this label block to create a compound block for our equation named implicit equation. We'll add one input pin for the x signal and one output pin for the y signal. Now we'll go inside the compound block and implement the equation as a difference equation. First, we'll create the yk plus 1 and yk signals using a unit delay block. From the block's time delay menu, select a unit delay, and from the block's signal producer menu, select a constant block. Set the constant block value to 1, connect it to the Boolean input of the unit delay, and combine these two blocks in a compound block named UD for unit delay. Using a variable from the block's annotation menu, label the UD output as y of k. Now let's get all the blocks we're going to need to implement the difference equation. From the block's arithmetic menu, we'll need a summing junction block, a gain block, a sign block, and a multiply block. From the block's annotation menu, we'll need a wire positioner block. From the block's Boolean menu, we'll need a not equal block. And finally, from the block's nonlinear menu, we'll need a merge block. Control-Shift left mouse to make two copies of the yk variable. Name one x of k, and name the other start pulse. Connect the variable xk to the compound block input pin. Control-Shift left mouse to copy the UD block. Connect the UD block to the xk to create x of k minus 1. Then, define start pulse to be set when xk is not equal to xk minus 1. Now we'll implement the difference equation. Trigger the merge with the start pulse variable. Set the true input to y of k. The merge output is, by definition, y of k plus 1 and connected to the UD input. The merge false input is produced by the summing junction times the gain minus 0.2. One input to the summing junction is connected to x of k. In the feedback loop, form yk squared, then form sine of yk, multiply them together, and connect this to the second input to the summing junction. This completes our difference equation implementation. We will create a for loop that will run our implicit equation compound block for 10 iterations during each simulation time step. Under the System Properties Range menu, the simulation time step is set to 0.01 seconds and the end time to 0.1 seconds. Control-Shift left button to make a copy of the implicit equation compound block. In the Copy Block Properties, check the Local Time Step option and set the value to 0.001 seconds. It is the ratio of the simulation time step divided by the local time step that determines the number of iterations the implicit equation will run during each simulation time step. Apply a constant block set to 5 to both compound blocks. Place a plot block on the screen. Pin the upper compound block output to the red plot pin and the lower compound block output to the blue plot pin. Click Go. The difference equation is solved when its output reaches a constant value. The red trace is the difference equation solution as it iterates once every simulation step. We can see it takes several simulation time steps for it to reach a solution. The blue trace is the solution after 10 iterations have been completed per simulation time step. we can see it completely solves at each simulation time step. To further illustrate the importance of this feature in a dynamic simulation, we'll replace the constant input with a slider set with plus or minus 10 upper and lower bounds. The simulation time step will remain at 0.01 seconds. We'll increase the end time to 10 seconds and select Run in Real Time. Click Go. Randomly adjust the slider during the simulation. The time lag between the blue and red lines is a numerical calculation time lag and occurs because the implicit equation has not been completely solved during each time step. Using the local time step compound block option provides one method for solving equations that require iterations for their solution.